demonstrated the first laser by taking a cylinder of ruby and surrounding it with a xenon arc flash lamp used in aerial photography. An intense burst of light from the lamp initiates lasing. To see how it works, let's look at what happens with a weaker lamp. A flash would promote a few electrons from the ground state to an excited state. They'd lose a bit of energy, fall to a lower energy state without emitting light, and then drop from there to the ground state, giving off a burst of light. The light produced would be incoherent light, a spectrum of colors and intensities, just as my small laser made the ruby sphere glow. To create a laser takes an extremely powerful lamp. In the ruby laser, repeated flashes, called pumping, make something amazing happen. They supply so much energy that a population inversion occurs. Here, more electrons in the energy level just above the ground state than in the ground state. Electrons from a population inversion returning to the ground state release light that starts an avalanche called stimulated emission. The photon produced when an electron decays induces other excited electrons to simultaneously decay and release nearly identical photons. That creates coherent light, meaning that the crests and troughs of every light wave in the beam match up. Now, at this point, we have coherent light, but not yet the other two properties of laser light. To get a narrow beam with all the light rays parallel and of a nearly single wavelength requires an addition to the ruby rod. Mayman silvered the ends to reflect the light within the ruby cylinder. He made the two ends of the rod astonishingly parallel to each other. From top to bottom, the distance between these two mirrors differs by no more than 200 nanometers. Inside this resonant cavity, two things happen. First, any light rays that don't line up with the axis eventually just exit out the side of the cylinder, and the light parallel to the axis becomes intensified and narrowed in wavelength. The mirrored ends create a standing wave, which means only light of particular wavelengths can exist inside the cavity. By choosing the rod length correctly, we can get the nearly single wavelength of light characteristic of a laser. A small hole in one of the mirrors, or a partially silvered mirror, allows